So, welcome everybody. This is sorry, this is ficonTEC's fourth webinar in 2020. Welcome everybody to the discussion. I am sharing the discussion today with CEO Torsten Vahrenkamp. We will be talking about our wafer level testing system developments. Kevin, please roll camera. Okay, then once again, welcome everybody. This is the fourth episode, 2021. I think I said 2020 before. This is the fourth episode this year so far. We will be looking at wafer level test development and update thereof together with Torsten Vahrenkamp. This is a hot trending topic with ficonTEC at the moment, and there is a lot going on with a lot of our customers at the moment. Just give me a moment to let in a few more people. Okay. We will start, Kevin, with the next slide. Oh, I'm sorry, Torsten, hello.
Hi.
I forgot to give you a chance to speak. How are you doing?
Very good. Hello, everybody. It's like very, very cool to be here again and yeah, be able to talk about that topic.
Actually, I think this is the fourth webinar you've taken part in so far, so yep. That's a good sign. You like them, obviously.
Yeah, I love them.
So, we start off with the giveaway. Don't forget the giveaway, Gregory. The giveaway today, or the question today is, what is the name of the experiment that may have found a new force in physics? So I don't want the name of the particles or the location. I want the name of the experiment where they have perhaps found a new force and they're looking to provide more concrete results with, I think it's 5 sigma they need to achieve. Answers, please, into the chat. And the person with the correct answer in the chat today will win a gift voucher from Amazon. So good luck in finding out the answer to that. Kevin, next slide, please. What is ficonTEC news? Well, we are hiring. We are looking for new people to join the team. We have a number of open positions. If you go to our website page that deals with careers, you will also find some on LinkedIn, I believe. You will find a list of positions that are open. If anybody is interested, or you know anybody who might be interested in working for a rapidly developing, growing high-tech company at the forefront of photonics assembly and tests, then you now know where to look. Second piece of news is we'll be having our next webinar on high volume manufacturing on April the 28th. That's in 2 weeks' time. We will be looking at systems for inline and high volume manufacturing that are available from ficonTEC, what the philosophy is behind the development of those systems. We will be looking at best practices and considerations with regard to high volume inline manufacturing of photonics devices, and looking at aspects such as, or aspects that affect throughput, yield, and tack rate, and all those considerations you need to have in mind when thinking about that route forward for generating your manufacturing process. Kevin, next slide, please. So we're now going to move on to the topic of today. I need to let in a couple more people. There are now still no answers in the chat for the question. Let me just repeat the question for the people who have joined. We have a giveaway for those who have joined. The question today is, what is the name of the experiment that thinks it may have found a new force in physics? Answers into the chat, please, and there is a giveaway voucher from Amazon for the person who gets that correct. So, wafer level test development update. What has led up to the current status of ficonTEC? We'll be discussing that together with Torsten Vahrenkamp, and what that status is, and what the immediate future looks like, what is the event horizon for new systems and new developments. We hope to cover all of those bases in the discussion today. Kevin, next slide. So optical testing to date, what is the pathway? And this is where we want to have a discussion as much with just as me talking. So it's discussions with Torsten. So what is the pathway that led us to this status quo to where we are today? Kevin, next slide, please. So first of all, at which points are we looking at in the production chain? We're looking at validation testing and verification testing in the product value chain or in the development workflow. These are located directly after R&D, for example, or during R&D, so effectively in your product and in your process development. And at a later stage in the workflow when you are looking at manufacturing. We have shown this slide before in previous webinars. I won't be dwelling any longer on this. It is there for completeness. If you want to have more information about any of the points in this slide, you can reach out to us at any point. Kevin, next slide, please. Torsten, what is the pathways you think, as you see it, that has led us to the status quo where we are today? What is it that we have already done in the testing environment in association with our other activities? What have we achieved? What is the status quo?
So first of all, I mean, as it's written here on the slide, we have over 950 machines now installed globally, and they are primarily on the assembly side of the photonics modules. So we're very well known in the area of the assembly, high precision bonding, active alignment type of activity. But part of our business was always the testing of individual chips we picked from wafer, tested electrically, optically, high power lasers, photonic integrated circuits, telecom lasers. All these devices were already things we tested. And it was only a natural progression to go to the wafer level testing of photonic integrated circuits, because we were asked by many customers if we can't do anything in this area, because everything was what was on the market is testers which can test semiconductor wafers electronically but not optically. So, and everything what you see today in the market is an electric tester and optical testers on top, but we go the other way around.
So, but if we take a step back again for a second to what you said a moment ago, so we've always included test functionality with our assembly systems. Either we've done that as midway in the process during the assembly process, or as end of line test. And we've done it not only on singulated dies and chips and systems, but we've also done it on gel pack delivered wafer. Yeah. So not exactly wafer level, but wafer handling formats we've had to deal with in the past as well, where you do pick and place, check the individual component, and then move it back.
And generally, when you have a device which you need to actively align, you need to drive and to read the signals anyhow. So next step is also at the end of the assembly process to do a quick test.
And I think it's fair to say that the amount of interest we've seen from some of our major customers in terms of being able to now in the future perform, let's call it EOS or electro-optical testing combined has been very significant, right?
So for us, I think right now it's our fastest growing section. I mean, the other things, other activities, we do have a stable growth, but the fastest growing right now is the electro-optical test, specifically on wafers.
Probably together with LiDAR as well, right?
Yeah, but is that right now the majority is on wafers and photonic integrated circuits.
What is it you think that enables us to take a holistic approach more than anybody else?
We know how to handle the components mechanically. We have the active alignment capabilities you need. We have the software, which is running on 950 plus machines worldwide, and the software doesn't need to be changed. And all this instrumentation you need to test the wafer is already integrated in our software. So for us, it's not a large step to go from the assembly side to the test side. For sure, okay. It's every individual customer has its own requirements, but generally it's part of our DNA.
Good, Kevin. Next slide, please. So that was the status quo. That was the pathway that led us to I guess it was about two and a half, maybe 3 years ago, that Ignacio, for example, then has actually put into the role of looking more intensely at the testing requirements in the market. What have we realized since that point in time?
No, Ignacio is pretty much the enabler for us and he was the person who always pushed me to do more in this area. What was always missing for us is the complex instrumentation you need to integrate to test such a wafer. So the usual game for us was, okay, we deliver the hardware, generate the software interface, and the whole instrumentation was delivered by the customer. We see that changing slowly. So that is the future. We will much more going, and we don't do that alone. We do that with partners into the instrumentation to test wafers entirely.
I mean, the software we have already has a huge library, right?
Yeah.
It can interface to a huge number of different instrumentation devices from different manufacturers. But what we want to do is we want to integrate a modular instrumentation into the systems at ficonTEC so that we can better integrate and deliver a better package. So that's one aspect of where we've moved forward over the last 2 years. But I was thinking more in terms of what are the systems that we have delivered already into the markets to specific customers, at least the ones that we can name.
The systems we have delivered evolved now also over the time. So there was, as you see on the pictures right now, the system in the center is a singulated die tester where the customer loads the wafer on tape. The machine picks and places the chips to 2 test stations. And today we see more the testers which are doing the tests on wafer. Now we see pretty much where we just got a larger amount of requests for a combined tester, a tester which can do wafers but can also do diced wafers already. So that is the sorting functions as part of the machine.
You were referring to just a second ago is that the picture on the top left, I think. The picture directly below that is from a system that we did with Southampton University in the UK.
Yeah.
At the University of Southampton 2 years ago, at the ORC there. That was, I think, one of the first. So it must have been exactly 2 years ago. One of the first wafer level test systems that we sent out.
Correct.
And since then, we've had other ones, right? There was VLC photonics was very recently.
Yeah, so the machine we delivered to VLC, which was a very important project for us. We're still working intensively with them to enhance the system. There are others. So right now we have total shipped 12 machines, and there's 4 right now in our production floor, which will be shipped soon.
Okay. The later iterations of the system are not just optical, but they also combine electrical testing so that you can do simultaneous electro-optical mixed signal measurements.
Yeah, so there's complex RF and DC probing combined with optical probes.
What are the structures that are being tested with these systems? What types of structure? Relatively simple, I imagine.
No, it can be. So first of all, in the beginning, it was only array couplers we were testing. Today, we see more and more structures where we need to have edge coupling to the devices. We have right now a tester we built where we need to come from one side of the chip, edge coupling, but at different locations.
We'll be looking at that later, yeah.
Yeah, so that's super complex. So you need 2 6-axis alignment engines from one side of the chip, and there's pretty much no space in order to test this wafer. So it's super complex, and we have solutions for that.
Okay, we take a look at that later as well. Kevin, next slide, please. What we want to do now is we want to have a look at where we have gone from that current status quo. Where are we going? What is the pathway moving forward? Who will we be working with? And what is the event horizon for things coming up? Kevin, next slide, please. So in volume testing for photonics, what are the hurdles? Obviously, we can go back and have a look at the semiconductor world. How has it been done so far? They have had the advantage that they've only had electrical only probe heads that are contact to 80 mu sized pads on the wafer. So low alignment requirements, but many thousands of pins, of course, on a single wafer, but they do the wafer in a whole shot.
Yep.
That is relatively straightforward. That still does not restrict the probe heads from being very, very expensive, because these things are then used for thousands and thousands of wafers, of course, right? So what are the hurdles for photonics? We have higher resolutions and accuracies that need to be achieved because we're now looking at achieving optical alignment as opposed to just electrical contact. So naturally, then we're looking at fast active or certainly well-sorted passive alignment so that we can achieve first light and then gain light into the couplers, whichever the couplers look like. And we also have the hurdle that we now want to combine optical and different types of electrical contact, both DC and low frequency and RF, into the tens of gigahertz, ideally into a single probe head, or at least if there's few channels, do that in parallel individually. And the task then is, of course, is to bring this all together into a suitable probe head design or a multi-element probe head design that allows us to do all of this in parallel. Otherwise, if we can't do it in parallel, then we cannot do it fast. Kevin, next slide, please. So, Torsten, well, what is it that needs to be tested? It's not actually quite so simple as it might appear on the last slide, right?
No. The things we are getting right now is manifold. So there's for sure the large section of telecom or datacom PICs. And this set was, I would say, that's the majority for us, which needs DC and RF testing, but very simple optical interconnects. Then there's PICs for LiDAR applications, for other medical applications, which have a completely different layout, how the waveguides are structured in the chip. So the way how you probe them optically, but also electrically, is varying a lot. Then the biggest challenge we have is the large variation of customers, because
right.
Usually the customers, they don't come with one design, they come with many different designs, and the machine needs to cover them all. And we cannot really dictate where customers put their electrical RF, DC, and optical pinouts. So we have to adapt the machine to this.
Well, there's zero standardization, I guess, of course, for combined electro-optical testing at the moment.
We work on with a lot of customers to try to, and also for the sake of more flexibility later on in the assembly, we have to generate standards, at least customer to customer, that say, okay, everything we do for this one customer has one kind of fingerprint. That's kind of has a certain flow of processes. Also from the data, how it's handled between the machines. But it's, for us as a machine builder, often pretty difficult to influence that. But we try to do that. The other thing we need to test is as VCSELs. VCSEL for various applications. Then we see an increasing demand of laser testing, again, which requires a completely different machine. That's not wafer level, but that we test all optical devices.
We're back to that question of design for manufacturing, aren't we, really, at that point, which is so often raised among standardization discussions, and where we can also take an active role with the customer in helping to develop that aspect of the production of product workflow. If we quickly run through some of the points here in this slide, what are the other hurdles? The devices are on a wafer, so it's no longer singulated dies. We want to measure multiple devices. The type of structure, as Torsten already said, can vary from simple to VCSEL to full transceiver type modules or LiDAR devices. And then within any one company, they can vary again. We want to measure not just light output, but LIV, maybe do beam and spectral characterization. For telecom devices, bit error rate testing, for example, there might be RF connections that need to be made, etc., etc. And of course, when it comes to parallelizing that whole game so that you can achieve higher speeds, so not just testing one component at a time, but moving up to ×4, ×16, ×64, then you get into issues of where to put your instrumentation, for example, as you get into the higher numbers. And then, of course, that all ties into what is the throughput you hope to achieve. And simply, it's not a straightforward task. And we have given a lot of thought to this, and we've also brought some partners into the project, which I think we get to see on the next slide. Please, Kevin. So effectively, the slide is titled Moving on to Mixed Signal. That is where this pathway is taking us. We're moving away from pure electrical measurement and pure optical measurement to, as much as possible, combined electro-optical mixed signal testing, which requires several different ways of looking at the problem and how and attempts at trying to solve the problem. Torsten has highlighted already, I think, what are the three main areas where we need to think in terms of what the solutions can be. These are singulated or non-singulated on-wafer devices, array structures, for example, PICs, waveguides, for example. Let's call this the version 1 type system. That can also be equivalent to the VLC and the Southampton systems we talked about earlier on in the webinar. Version 2 is then where we have VCSEL testing, again on wafer. Sorry, this is fundamentally from what is tested is relatively simple. You're looking at LIV, you may be looking at spectral and beam characterization. There's no RF. You're testing output, you're testing functionality, but it's very repetitive. And if you do it singly for thousands and thousands of VCSELs on a single wafer, it's going to take you a lot of time. So you really want to parallelize the operation. So you really want to have multiple testing capability within a single probe head. So times 4, times 16, times 64. And it's at the higher numbers that you really start achieving higher throughput for any one particular wafer. And then the level 3 approach is for much more complicated devices, PICs or modules, where we want to do full electro-optical input-output testing. As Torsten has already highlighted, this is much more diverse and complex. There is much more sub-micron fast-active alignment, active alignment required for certain application areas, optical interconnects, and there's probably going to be RF issues that we all need to consider. And what is common to all of these mixed signals, so combined electro-optical input-output, we can want to have a solution that can cope with singulated or non-singulated on wafer or wafer level handling types of tasks. At any of these 3 levels, we want to be able to perform full electro-optical performance verification. We want to include the instrumentation, and we want to be able to support all optical coupling schemes, which we will come to. We will come to some of these points in a moment.
I just want to highlight one thing, Greg, and these 2 logos. This T3. It's a JRC, a joint research activity we do with Politecnico Milan, ficonTEC, and Photonics 42. So this is actually tackling specific non-existing instrumentation for either VCSEL testing or the PIC testing. So I'm super happy that we started this activity. There's already very nice outcome. We are testing the first devices already with these electronics. The Politecnico Milan will get a wafer tester from ficonTEC to accelerate these kind of investigations.
And as much as possible, it's working together with these companies. We're looking at the whole holistic approach. It's not a case of just creating a system and then adapting it. We need to adapt the software. We need to have the hardware. We need to develop probe heads. We need to think about what are the strategies for testing multiple systems at the same time on a single wafer. There's a whole bag of ideas and aspects here that need to be considered all at the same time. And thank you for highlighting those logos. You beat me to the point I was just about to ask you to detail the relationship with those people. Thanks. Kevin, next slide, please. I'm just going to include this slide here for completeness. I won't be talking about it very much. Effectively, we will need to work with the main manufacturers for instrumentation, some more than others, depending on what is available. But we will need to think about how we are going to handle multi-channel data acquisition over multiple chips on wafer, and how that data is measured, captured, and then of course handled and stored.
small correction, because we don't need to. We do that already because we're pretty much instrumentation out or machines out with every single company you're mentioning here. So with Quantify Photonics, which was before Coherent Solution, which is on the picture, we have systems developed. We have a lot of stuff from National Instruments integrated in our systems. We have the Keysight systems. We're using a huge amount of Keyslay instruments and also Expo. And it's all integrated in the software.
But those are integrated with the software, but the challenge is when you do this at that times 16 and the times 64 level, right?
Yeah.
Okay, one quick aside, we have a correct answer in the chat from, oh, surprise, surprise, from Maureen. Maureen, you will be receiving the voucher. Kevin has your address already, so thank you for the correct answer. That answer is the muon G2 experiment. And we have a question in the chat, Greg, why that has been around for more than 20 years? That's a very good question. I'm not going to answer that right now. Next slide, please, Kevin. VLT version 1, combined electro-optical test, input-output test for on-wafer devices at the single chip, single die, single device level. Kevin, do you want to quickly talk us through these 4 pictures? What are the basic elements of the VLT in the version 1 type?
Do you ask Kevin or me?
Did I say Kevin? Torsten.
Yeah.
I'm sorry, Torsten.
I think Kevin was now very surprised.
Kevin can have a go if he likes.
So the upper left corner shows actually the fully integrated machine in the housing. But if you go to detail, there's one of the main component is the wafer table, which goes up to wafers of 12-inch. There's a Z-head, which is carrying an optical distance sensor, and also the camera, which allows us to detect the structures on the wafer, to have a full automatic detection of the areas we need to probe on the wafer. There is a bottom side camera on the wafer table, which is actually there for system calibration. The machine is running fully automatic. So you load the wafer can be rotated and positioned in XY underneath the electrical probes. And this process runs fully automatic. And the indexing from one device to the other is also full automatic. Rear side or north-south full DC or RF probing capabilities. RF probing is a little bit more complex because you need to wire the heavy cables out of the system, which then need to be connected to the amplifiers or to the instrumentation. And then the lower right picture shows these 2 6-axis aligners, which are ficonTEC proprietary technologies. So they align the optical interfaces to the chip.
If I black out and don't say anything, it's because my internet connection is not so good. So just be patient. I should come back online if I disappear for a moment. Thank you, Kevin. Next slide, please. So what we can see in these pictures is we can see actually either it's the bottom left, for example, and then we're looking at 2 single fibers aligned over a wafer, I think in the green picture. So these are just some example pictures of what the close-up action is going on directly over the wafer. In the green picture, then we can see not only the optical test, but also the electrical test probe coming in from behind
in this case, it's a
alignment system.
In this case, it's a super simple DC test, but we're building right now a machine with over, I think, 500 electrical interconnects. So that's a different challenge.
But that's not version 1 of the WaferLine Test systems, though, is it? That's going to be the version 3, I guess.
Yep.
Okay. Kevin, if we go to the next slide, I think Torsten mentioned this already. We have machine vision systems built into the ficonTEC testing systems, and these are for machine alignment, registration purposes, but also for finding connections, finding paths, finding waveguides in this case, finding elements and finding chips, locating them properly, and building them into the coordinate system within the software, so that we can quickly use, so that we can use the motion system efficiently in moving to the individual chips, dies, and waveguides. And here in the top set of pictures, we can see how the machine vision system has identified where the wafers are, and this helps improve the fiber alignment in terms of finding first light at those waveguides. And then the row of pictures beneath is something that Torsten touched on in an earlier slide. And that is, Torsten, would you like to take over the discussion here?
Yeah, so the earlier wafer level test that we built was all like grating coupler based. So we were aligning two fibers or fiber arrays to the top of the PIC. Today, pretty much every single machine we're selling, we're using the specific printed periscopes. So it's actually a method which is lithographically generated structures on a fiber array, which allows us to bend the beam from the waveguide up into the fiber array, and it works beautifully because our whole vision system is hooked up to that capability.
And these are polymer periscopes that you 3D print onto the bottom of the fiber, right?
Correct. Yeah.
And I think they have. It's not actually on this image here, but we're looking at facets that are more or less 20 microns across. I think that are aspherical.
The trenches needs to be like minimum 20 microns deep, right. 20 microns wide in order for us to get in there. And we need to get in and then still align the array to the waveguides. So the active alignment is the same as we do on the grating side, a little bit more accurate, not only a little bit, but significantly more accurate. And the challenge is not to destroy the periscopes while you dive into the groove. But it works.
Right. Very good. Very good. And of course, we can do this over multiple channels. I believe the facets are aspherical in form as well, right? It's a case of once you've programmed the growth through the lithography process, it doesn't matter what type or how complex the surface is. Once you've programmed it, it's just a rinse and repeat process. So they use aspherical surfaces here to enhance the coupling efficiency from the mode field coming out of the waveguide.
Yeah.
Okay, so I think in the next slide now, Kevin, if you can just stop the video for a moment. We have a comment or a question in the chat that maybe we can address now, Torsten, together. What is this? This is a question from Mike Wong. Mm-hmm. What is the single biggest challenge now facing photonic manufacturing, particularly at wafer level testing, given the fact that it's extremely challenging at wafer level? As you may be aware, high volume manufacturing, or HVM, is highly essential, coupled with the fact the configurations keep changing at the customer side. Do you already have customers adopting this type of testing or approach at a higher scale?
So the majority of, so we have one customer who is doing it on larger scale, but the majority of our customers still do multi-project wafers, which makes the handling of the machine even more complex because you need to adapt within one wafer structure different PIC structures. So, but is that there's customers which have like a larger number of dies.
I think an additional answer to that question is that yes, we do have customers that are adopting this because we are working with some of our most important customers to actually develop these systems together with what their actual needs are. We're not just doing this work on our own independently of what the industry really needs. We're working with the community to establish what is the best way forward. I hope that answers your question, Mike. Kevin, then please let the video roll, and we can quickly talk over this. But it's effectively just highlighting what we've discussed already. This is a placement of the wafer onto the chuck. You center it. Of course, it's held by vacuum. Once it's placed, it's thermally controlled. And then you go through an automatic process of finding out where all the different devices are using the machine vision system. So setting up the references. And the optical probes can then move over the chip together with any electrical, if that is needed at that point. And there's a simultaneous dual fiber alignment that takes place into the input-output ports, whatever they may be. And we can establish using fast automatic routines, fast light, And we can do this not only for single fibers, but we can do it for fiber arrays. And also, as we saw in the previous slide, we can do it for 3D printed tips on the end of fibers arrays, putting the fibers down into trenches. Okay.
And
Kevin,
after Corona, I can pretty much, would love to invite everybody to have a look. This machine's live and in color. Much more impressive to see that, especially with the little periscopes diving into this super small grooves.
Well, with hopefully there will be some news coming out in the near future. ficonTEC is celebrating its 20th anniversary this year, and we still hope to be able to celebrate that later in the year, maybe with an open day at ficonTEC. So let's see if that is something that can be realized once this is at least largely over.
I thought you had some news about COVID.
Sorry, I don't. Not any good news anyway. Okay, so Kevin, next slide, please. Version 2 of the WaferLine testing system is the adaptation for VCSEL testing. And we want to do this as much as possible at not just at the ×1, but at the ×4, ×16, ×64 level. Torsten, what are the aspects here that we have had to think about?
There's many companies out there who develop and sell probers for VCSELs, which test one individual VCSEL at a time. If you have a larger wafer with VCSEL, there's easy like 200,000 VCSEL on one wafer. If you can reduce the number of probes by having multiple devices simultaneously and having the possibility to also optically test those devices, that was our approach. So what we have established now is in the lab now, and also one at the customer side has a 16 probe system, so we can test 16 individual dies already, and the whole testing is done with an optical switch. So and what you see in the corner, in the upper right corner, is the electrical probe is with all the optical interconnects. So that's something what we have established, and it's working very nicely. We can do LIV, we can do spectral tests with the VCSELs, and it's impressive to see because it's super fast. We can go down to this 200 millisecond per device.
But we've had to think about issues about how do we avoid crosstalk. I mean, we won't go into details about how we solve those problems, but you have to think of when you're testing VCSELs next to each other on the same wafer.
We did a lot of proof of concepts, starting in the lab with some individual devices, but it's all now established, and you can buy these systems from ficonTEC.
And this has been in close collaboration with Polytechnic Milano and with Photonics 42, of course, who have played a great role in helping us reach this point where we are with this type of system.
And again, thanks to Ignacio, I was very much pushed into that direction. I'm very happy about it. Okay.
Very good. Then next slide, please, Kevin. So what is it that the viewers or anybody else looking at a later date will need to know about this type of system? So the WaferLine Test System version 2 or variant 2 is, so we're now testing with and increasing furthering developments with particular customers. We're looking at very much that is what is a VCSEL oriented probe head configuration in ×4, ×16 or ×64 configurations, so that you do parallel testing. This is for non-singulated VCSELs on wafer. We're looking at full parallel mixed signal electro-optical performance verification. Instrumentation is on board, and the release time frame, I think you said to me earlier today, Torsten, is July, August. Is that correct?
Yeah, we have the first, we have the system in test right now, and that release time will be July, August.
And you also mentioned something about Nanofoot earlier today.
Yeah, so that was the Finnish company Nanofoot, mainly known for inspection systems and LIV tests. So there was a little bit of overlap with what ficonTEC is doing already also for a long time, but they're specifically good at their burn-in systems. We took over their whole product line, and we are integrating it right now into the product line of ficonTEC. So it's not only that we are extending our activity in the in the area of the pick on wafer, but also in the direction of testing the whole module or the laser on submount in a burn-in rack, like thousands of them in this rack. So we're starting this activity in our facility in Estonia. We are completely building a new team who is then responsible for this burn-in acquisition we did with from Nanofoot.
And with that, we're back to the aspect of ficonTEC taking a holistic approach to the whole production process development workflow, and where we can be active in each of those sections along that pathway. And
specifically the interconnection of all these machines, like the whole data management. That there's one manufacturing engineering system which is hosting all this data. That we have a revision control overall machines. So it's not only individual machines anymore. We are offering the whole the one-stop shop, including data communication between all these machines, which is everybody who has done that in his own factory. It can be a very painful process.
And there we're back to the fact that we have a webinar in 2 weeks' time on high volume manufacturing and inline systems on the 28th of April. Kevin, next slide, please. So, and then the third version of this of the WaferLine tester system, Torsten, is what are we trying to look at there? What are we trying to cover with the developments there?
So if you look at the wafer level tester, how we see it today, I mean, it's mainly a characterization of devices. If you want to see it a little bit further, how you test wafers in the semiconductor industry, it's a completely different approach. You pretty much probe the whole wafer and you test everything in one shot. So we're far away from this process, but it's something which we think about, and we are working on concepts how to do that in future.
The other aspect here, of course, is we're looking at much more complex hybrids, maybe co-packaged systems, of course, right? Modules where there are, you mentioned earlier, we're working together with one company where we're putting together a system where we're going to be looking at 500 channels simultaneously.
Correct. And this is always more, also like kind of more module level, which has a very strong demand on the RF probing, DC probing, optical interconnects, temperature control, because that is already environmental testing and built into the system. So that's another dimension, which also then goes already a little bit more into the burn-in of the system's data.
Maybe a difficult question to answer at this point, and if you don't have the answer, don't give one. But when we are at the point that we are measuring 500 assorted channels out of a single module, I mean, there are vast instrumentation issues that need to be addressed at that point. Another question, of course, is that something that can happen in parallel, testing several devices at the same time?
We don't have the request right now, but potentially I can see that coming.
Okay. And again, there I note down some points. What is it that potential customers would need to know? This, of course, has a somewhat longer time frame, probably until it's released. I don't know if we want to say anything at that point, but we are looking at much more bespoke probe head design, much more complicated probe head design, of course, with that number of channels. But the application areas here, of course, are in the optical interconnects, and anything equivalent to that that's using co-packaging approaches to develop their modules, for example, like LiDAR.
For us, it's a different dimension of machines. So it's testing, but we don't unless it's a pick based LiDAR. The testers look different.
Good, Kevin. Next slide, please. And then, of course, there's there's a question of what exactly can be tested. I mean, we talked about LIV and spectral and beam characterization for VCSELs, but obviously, when you're starting to look at optical interconnects, then there's a much higher level of test that you can perform. Is this something that you want to highlight at this point, Torsten?
That is pretty much exactly what I mentioned earlier. The joint development in the JRC, which we are doing with Politecnico Milan and Photonics 42, is going exactly in this direction. So how will we be able to test very fast, not only one modulator on a device or one pin diode or one component at a time? I want to have the full pick fully tested in the super short time. I need to tune my ring resonators. I want to take the information out. I want to store it to a lookup table for this chip later. So all these kind of things need to be done in a very fast way and totally interconnected with the machine itself. So that is actually the way where we want to go.
So it's another dimensional depth to the challenge that we are trying to address.
But as I said, this will be very, very depending on the customers.
Kevin, next slide, please. And well, I guess when we're talking about potential devices that can have up to 500 channels, then obviously those devices are going to be very complex. It's not as straightforward as a VCSEL or a simple waveguide or array. And this is an indication of how complex those electro-optical devices can be that we want to be able to test. Any other thing? Do you have any other comments?
No, that's just like as it can be super complex, and that needs to be tested very fast.
Right. Very good. I believe that is the end of the main topic of the contents. Yes. So we're now going to move over to the roundup. If anybody has any questions that they would like to add to the chat, please feel free to do that. This is an opportunity to get a live answer from, well, mainly from Torsten probably. Maybe from myself in answer to a question. If we can't answer any questions right now, then we will, of course, be more than happy to get back to you. So if you have any questions, please do put them in the chat and we'll try and address them now. Otherwise, I will go ahead. So we've had a winner for our giveaway this time, a repeat winner. Thank you, Maureen, for providing the right answer. Now I'm going to round up the webinar for today. So very briefly, for the people who are not new to this process, what are the goals of the webinars? We try to keep these short, bite-sized, so that they don't take too much out of your day and out of our day. This makes them guilt-free. It also means it's an agile format, so we can improve our game if we get the right inputs, if we get feedback, and if we get new ideas. And we have those coming in as well. We had an interesting webinar 2 or 3 weeks ago where we had 2 external partners come in to help us with the content. And this is a format that we will be repeating, for example, in 2 weeks' time on high volume manufacturing, when we will have a partner company or a representative of a partner company come in, Frank Baumann, to help us to discuss the high volume manufacturing aspects that you need to be aware of. What you tend to hear and see within these webinars, during these webinars, is news and developments. Obviously, the products and the technologies and the developments that are happening within ficonTEC and within our ecosystem. And there is an opportunity for questions and answers. Kevin, next slide, please. The scheduling is random. It's always on a Wednesday. It's always 3 o'clock CET. If you go to our webpage, then you can take a look at some of the previous webinars that we have held. 2 together with Torsten are freely available. Others you will have to register, but you people know that already. That is the schedule for different parts of the world. Kevin, next slide, please. If you want to find out more about ficonTEC, the first point of call would be, well, ideally, you would call us up and speak to us directly. Alternatively, you can go to the homepage, you can go to our blog page, you can follow us on LinkedIn and Twitter. We have a Vimeo and YouTube presence where you will find snippet videos and longer videos designating and illustrating process capability. So little in the way of animations and very much and lots of material in the way of real video process acquisition. And there was something else I'm going to say, but we've moved on to the next slide already. Those are our points of presence around the globe. If you look at the locations page on our website, you will find out how to reach us. And Kevin, next slide, please. I think that should be the last one. Thank you to everyone. Torsten, thank you for your time.
Thank you very much. It was a pleasure.
Kevin, if you could quickly cut the feed. Torsten, thank you very much for your time. I hope that was useful. I hope that was useful to everybody else who's here with us. And many thanks, of course, to Kevin in the background for handling the logistics of rolling the webinar. Thank you, and we hope to see you again in 2 weeks' time. Thank you.
Thank you. Bye-bye.